Okay, so class, we're going to continue our discussion about the shortest path algorithm. I think we ended up here last week. So again, we are trying to find the shortest path from vertex 1 until vertex 7. Okay? So for example, for this one, okay, so we have an arc or an edge from vertex 1 into vertex 7. Okay, this is the arc, and with a weight of or length of 14. Okay, so next, so we have to look for another path from 1 to 7. Now, from vertex 1, okay, going to vertex 3, okay, this is 1. Then from vertex 3, going to vertex 6. And then from vertex 6, going to vertex 7. Now, if you're going to check the length from vertex 1 to 3, 6, 7, the length is 2 plus 8 plus 1, that would be 11. Okay? Next. So, from here, class, okay. From here, class, of course, you're going, if you're going to select the shortest path, you're going to look for the least value. So, the least value is from compared 14 compared in the value of 11. Of course, I'm going to select the path length of 11. So shortest path problems, single source, single destination, single source, all destinations. So all pairs, every vertex is a source and destination. So single source, single destination. So possible greedy algorithm. Leave source vertex using the cheapest or shortest edge. Okay, so you're going to look for the shortest edge. Next, so if we're talking about the shortest edge, we're talking about the length or the weight of that edge or arc. So next, leave the new vertex using cheapest edge, subject to the constraint that a new vertex is reached. Continue until the destination is reached. So let's check about this one. So a while ago, from the previous two examples, we tried to locate a different path from 1 to 7. So trying to find the shortest path. Now we're going to try to apply the greedy shortest path. Okay, so what's the difference between the greedy shortest path? As you remember, when you say greedy, we're looking for the best. Okay, so what you see best. So you're going that's what you're going to select. Now, since we are looking for the shortest, we are going to select by means of greedy. So to select greedy through greedy algorithm, so starting with the vertex 1, okay, I am going to look for the least value from vertex 1. So comparing the values from vertex 1, I have 3. I have 2, I have 16, and I have 6. So I want to get the cheapest value of all of the out of 3. So the cheapest value from 2, 16, and 6, I will select 2 because this is the lowest value. So meaning to say, from vertex 1, I will go to vertex 3. Okay? Now, for vertex 3, I have 3 options again. Okay? So applying the greedy. So from greedy, from vertex 3, I have a length of 8, I have a length of 3, and I have a length of 7. Now again, applying the greedy algorithm, I will select the cheapest. Okay, since we are looking for the shortest value or shortest path. Okay, so the shortest is what? Compare 8, 3, and 7. We're going to select what? We're going to select 3. Now, moving on to from vertex 3 to vertex 5. Okay, so from 5, let's check. we can choose from different two edges. So the two edges are, we have 10, okay? And then we have a length of 4, okay? So again, applying the greedy algorithm. So since I am looking for the shortest path, so I'm going to select the least or the cheapest value, which is 4. Okay, so now from the vertex 5, I am going to move into vertex 4. Okay, from vertex 4, how many edges do we have to, can we choose, do we have to choose? Okay, we only have one. So from vertex 4, we only have the edge that has a length of 3. Okay, so now this is the path from vertex 1 into vertex 7. If you are going to add it up, 2 plus 3, so 5 plus 4, 9 plus 3 is 12. So if you are to compare the previous results before from the shortest path algorithm, we have, if you remember, we have what? We have 14, we have 11, and we have 12. So using the greedy algorithm here, 12 is not the least value compared to 14, 11, and 12. So since 12 is not the shortest path, so algorithm doesn't work here. So meaning to say the greedy algorithm did not work in the shortest path. Okay? You understand, class? Okay, moving to the next slide. So now, single source all destinations, so need to generate up to n. So n is the number of vertices or nodes. Okay? So greedy method con- construct this up to n paths in order of increasing the length. So assume edge cost lengths are greater than or equal to 0. So no path has length less than 0. So first shortest path is from the source vertex to itself. The length of this path is 0. Okay? So again, so let's check the single source all destination. So from vertex 1, okay, from vertex 1 here, so we don't have any incoming edge, okay? So that's why we have the length of 0. From vertex 1 to 3, okay, from here going to 3, we have an edge or arc with a length of 2, okay? Next, so the next path is 1, 3, and 5, checking the graph. So 2, so 1 to 3 is 2, and 3 to 5 is 3. So we got 5. Okay? So next is what? We have the vertex 1 to 2. Here, from here, vertex 1 to 2, we have edge with the length of 6. Okay? Next, from vertex 1, 3, 5, and 4. Okay? So, to sum it up, 2 plus 3, 5 plus 4, we will have 9. So, the length is 9. Next, from vertex 1 to 3, okay, we have 2, and then 3 to 6, we have the length of 8. So 2 plus 8, we will get 10. Okay? Next, from vertex 1, 3, 6, 7. Okay? So vertex 1 to 3 is 2. 3 to 6, we have a length of 8. And then 6 to 7 is 1. So 2 plus 8 is 10, plus 1, we will have 11. Okay, so this is the greedy single source all destinations. So again, we only consider the path from vertex 1 to vertex 7. Okay, just to summarize again, so this is a summary. So we have the path and then we have the length. So 1, 0, 1 to 3, vertex 1 to 3 is 2, vertex 1 to 5 is 5, vertex 1 to 2 we have 6, and then vertex 1 to 4, we have length of 9, and then vertex 1 to 6, we have the length of 10, and then vertex 1 to 7, we have a length of 11. Okay? So next, greedy single source all destinations. So let di as the distance from the source be the length of shortest one edge extension of an already generated shortest path. The one edge extension ends at vertex I. Okay, the next shortest path is to an as yet unreached vertex for which the D value is least. So let P be the predecessor, be the vertex just before the vertex I on the shortest one edge extension to I. Okay, let's have an example. Okay, we are going to use the same graph. Okay, now using the vertex 1, okay, here, using the vertex 1 here, okay, so from vertex 1, do we have any edge looping to itself? No, that's why we have 0. Okay, so we were talking by, again, D is for the distance, P is for predecessor. Next, okay, we're still on vertex 1. So vertex 1 to vertex 2. From vertex 1 to vertex 2, we have a length of 6. Okay? That's why we have 6 here. So 6 is the distance or the length. Okay? Next, from vertex 1 to vertex 3, we have a distance of 2. That's why we have the 2 here. Okay? Next, from vertex 1 to vertex 4, we have a distance or length of 16. That's why we have 16 here. Next, from vertex 1 to vertex 5, do we have any direct edge going to vertex 5? No. That's why we have a dash here. Next, from vertex 1 to vertex 6, do we have a direct edge? No. That's why we have a dash here. Next, from vertex 1 to vertex 7, okay? So we have a distance or length of 14. That's why it is 14 here. So class, the predecessor here is the actual vertex. Okay, so since we are only considering right now the vertex 1, so that's why we have 1 here, 1, 1, and 1. So the 1 is our predecessor. Okay, so let's move on to the next slide. Okay, now, so we're done with the first vertex, which is 1. We're going to move to the path from vertex 1 into vertex 3. Okay? So now, so again, is there any edge from 1 to 1? No, so that's why we will put 0. The distance is 0. Okay, next. From vertex 1, okay? From vertex 1 to 2, do we have any distance or length? Yes. We have 6, okay? That's why we have 6 here. Next, from vertex 1 to 3, okay, we have 2. That's why we're going to put 2 here. Next, from vertex 1 to vertex 5, okay? So vertex 1 to 5. Now, again, considering here the vertex, we have 1, 3. So vertex 1 to vertex 3 is 2. Next, vertex 3 to vertex 5 is we have a distance of 3. That's why we will get a total of 5. Okay? Next, from vertex 1 to vertex 6. Okay? So again, so considering this one, So vertex 1 to 3, we have 2. And then 3 to 6, we have 8. So we will get a total of 10. Okay? Next, from vertex 1 to vertex 7, okay, we have 14. Okay? So that's the length. So again, now, as you can see here, the predecessor is still 1 for vertex 2, for vertex 2, 3, and 4, and 7. While for the vertex 5 and 6, we use the vertex 3. Okay? Okay, moving to the next slide. Okay, now we're done with the pass from vertex 1 into vertex 3. Now we're going to move to path from vertex 1, vertex 3, vertex 5. Okay? So this one, we're going to use this one now. So again, vertex 1 to 1, so we don't have any distance. So we're going to put 0. Next, vertex 2. Okay, from vertex 1 to vertex 2, we have a distance of 6. That's why we have 6 here. Next, vertex 1 to vertex 3. Okay, we have a distance of 2. That's why we have 2 here. Okay, and still our predecessor is vertex 1. Okay, next, from vertex 1 to vertex 4. Okay, so from vertex 1 to vertex 4, since our path is from vertex 1, 3, and 5, we have to consider that, okay? So we're going to use this path. So from vertex 1 to 3, okay, we have 2. From vertex 3 to 5, we have 3 again. And then from vertex 5 to vertex 4, we have 4. So 2 plus 3 is 5 plus 4, we will have 9. So now, our predecessor is vertex 5. Okay? Next, from vertex 1 to vertex 5. Okay? So again, vertex 1 to vertex 5 is vertex 1 to 3, and then 3 to 5, we have the length or distance of 5. So again, our predecessor is vertex 3. Okay? Next, from vertex 1 to vertex 6. Okay, so what is our predecessor? So our direction would be vertex 1 to vertex 3, which is 2. And then vertex 3 to vertex 6, we have 8. So 2 plus 8, we will have 10. And of course, our predecessor is vertex 3. Okay, next, vertex 1 to vertex 7. So vertex 1 to vertex 7, we have a distance of 14. And again, our predecessor is vertex 1. Okay, now we're done with the path from vertex 1, 3, and 5. Okay, next. Now, we're going to move to the paths from vertex 1 to vertex 2. Okay? So again, checking the distance and the predecessor. So 1 to 1, we don't have a loop. That's why it is 0. Vertex 1 to vertex 2, of course, we have 6. Okay, that's why we have the 6 distance here, and the predecessor is vertex 1. Okay? Next, from vertex 1 to vertex 3, again, we have a distance of 2. And again, our predecessor is vertex 1. So that's the vertex before the latest vertex. Okay? Don't forget about that. Okay, next. Vertex 1 to vertex 4. So again, we have what? We have 9. So vertex 1 to 3, we have 2. And then vertex 3 to 5, we have 3. And vertex 5 to 4, we have 4. That's why we have 9. And the predecessor is vertex 5. Okay, next, from vertex 1 to 5. Okay, vertex 1 to 5. Okay, so again, vertex 1 to 3 is 2. And vertex 3 to 5 is length or distance of 3. So we have a distance of 5. And the predecessor is vertex 3, which is the previous vertex before the actual vertex. Okay? So next is vertex 1 to vertex 6. So again, vertex 1 to 3 is 2. Vertex 3 to 6 is 8. Okay, so the total distance is 10. So of course, the last vertex or the previous vertex is vertex 3. That is our predecessor. Okay, next. So again, vertex 1 to 7, okay, our length is, or distance is what? 14. So the previous vertex or the predecessor is vertex 1. Okay? Moving to the next slide. So now we're done with the path vertex 1 to 2. We're going to move on to vertex 1, 3, 5, 4. So this is now our direction. Okay? So again, we're going to check the distance and the predecessor of each vertex. Now, from vertex 1, we don't have any loop, so there's no distance involved. We're going to put 0. Next, so vertex 2, let's check. Again, we have a distance of 6. That's why we have 6 here. And again, our previous vertex is vertex 1. Next, from vertex 1 to 3, do we have any length or distance? Yes, we have 2. So again, 2 is our distance. And of course, the predecessor or the previous vertex is 1. Okay? Next, vertex 1 to 4. So again, we're going to consider this one, this direction, which is the vertex 1, 3, 5, and 4. So now, considering this, okay, this one, so we will have a distance of 9. And of course, our previous vertex is vertex what? 5. So that is our predecessor. Next, from vertex 1 to vertex 5, okay? We have from here until 5 only, we have 2 plus 3, we have a distance of 5. And the previous vertex is what? Vertex 3. So 3 is our predecessor here. Next, vertex 6. Okay? So for the vertex 6, what is our vertex? So we have 10. So 1 to 3 is 2 and 3 to 6 is 8. So we will have 10. And our previous vertex is 3. So this is our predecessor. Now, for vertex 7, okay? So considering this one, considering the direction of vertex 1, 3, 5, 4, okay? So vertex 1 to 3 is 2, vertex 3 to 5 is 3, and 5 to 4 is 4, okay? And then 4 to 7 is 3. So checking this one, 2 plus 3 is 5, plus 4 is 9, plus 3 is 12. Okay, just follow this direction, okay? So you're not going to be misled. Okay, now the previous vertex is what? What is our predecessor? Vertex 4. Okay? So this is the really single source of all destinations. Okay, next. We have a different direction now, which is 1, 3, and 6. So vertex 1 going to vertex 3, going to vertex 6. Okay? So vertex 1 to vertex 1, we don't have any loop. So the distance is 0 and we don't have any predecessor. Next, from vertex 1 to vertex 2, again, We have a distance of 6. And our previous vertex or predecessor is vertex 1. Okay, next. From vertex 1 to vertex 3, we have a distance of 2. And our previous vertex is vertex 1. So thus, this is our predecessor. Okay, next from vertex 1 to vertex 4. Okay, so vertex 1 to vertex 4, we have 9. Okay, so that's vertex 1 to 3 is 2, 3 to 5 is 3, and 5 to 4 is 4. That's why we have 9. And of course, the previous vertex here is vertex 5. This is our predecessor. Now, for vertex 5, so vertex 1 to 5, okay? So 2 here, we have a distance 2 here, and from 3 to 5, we have a 3 distance. So now, 2 plus 3, we have a distance of 5. So our previous vertex is vertex 3. Thus, vertex 3 is our predecessor. Okay? So next, vertex 6. Okay? So following the direction, 1, 3, 6. So 1 to 3 is 2, 3 to 6 is 8. Thus, we will have the distance of 10. So our previous vertex is 3. So thus, our predecessor is vertex 3. Okay? Now, for the vertex 7, so following this direction, so 1 to 3 is 2, vertex 3 to vertex 6 is 8, and vertex 6 to vertex 7 is 1. So 2 plus 8 plus 1, we will have 11. And now the previous vertex is vertex 6. Okay? So thus, vertex 6 is our predecessor. Okay? Just to summarize, class, so this is our summary. As you can see here, we have different directions here, and of course, the distance involved or the length. So we have the length of 0, 2, 5, 6, 9, 10, and 11 based on the given direction of the vertices. Okay? So single source, single destination, terminate single source, all destinations, greedy algorithm as soon as shortest path to desired vertex has been generated. So when do greedy algorithm work? Okay, so greedy algorithms are easy to understand and to code, but do they work? For most optimization problems, all greedy algorithms tried do not work. Okay, so but some problems can be solved optimally by a greedy algorithm. So the proof that they work, however, is subtle. So next topic is minimum spanning tree. Okay, still this is under the greedy algorithm. So example problem, you are planning a new terrestrial telecommunications network to connect a number of remote mountain villages in a developing country. The cost of building a link between pairs of neighboring villages has been estimated. You seek the minimum cost design that ensures each village is connected to the network. So the solution is called a minimum spanning tree. Okay, so there are times that it is the minimum spanning tree or the MS tree is called as the minimum cost. Okay? So it may be, MST may be defined on Euclidean space points or on a graph. So graph is equals to vertices and edges, weighted, connected, and directed graph. Okay, spanning tree is equals to T, and then T is a sub-element of undirected tree. So we have the minimum spanning tree, a spanning tree with the smallest total weight. Okay. So we're going to look for the smallest total weight. So this is an example of a minimum spanning tree or minimum cost spanning tree. So we have a graph here, okay? Now again, we're looking for the minimum cost. So this one is an undirected graph as you can see on the screen. So check vertex 1. From vertex 1, you have three different edges. We have 10, we have 45, okay, we have 30. So you have to select what is the minimum cost or weight or distance or value of the edge. So upon checking here, 10 versus 45 versus 30, of course, if I am looking for the minimum cost, I will select 10. So thus, from here, from vertex 1, I will go directly into vertex 2. Because vertex 1 to vertex 2 is the lowest cost. Okay? Now, let's try to check vertex 2. From vertex 2, I have three different edges again. So I have a weight of 50 or a cost of 50. From vertex 2, I have a weight or a cost of 40 going to vertex 5. Okay? From vertex 2 going to vertex 6, I have a minimum cost here or weight of 25. So now, comparing the values, I have 50, 40, and 25. What will I select? Of course, I will choose the lowest value, which is 25, right? Thus, I am going to select the edge from vertex 2 going to vertex 6 because vertex 2 to vertex 6 is the lowest cost, which is 25, okay? Now, from vertex 6 going to vertex, from vertex 6, I have I have four different edges, okay? I have 20 here. So 25 is not counted already because we already used the edge, okay? And then I have 55 here and I have 15. So what will I select? So class, if you're going to check the graph, we have to visit all of the vertex. Okay? If I am to compare from vertex 6 going to vertex 4, I only have one edge. So thus, I will get this edge. Okay? So from vertex 6 to vertex 4, I have this one because this is the only vertex, the only edge connecting to vertex 4. Now, from vertex 6, okay, from vertex 6 going to vertex 5 or 3. So I have two values here. So we have 55 and 15. So 15 is the lowest cost. Then I will use the edge of vertex 6, okay, into vertex 3 because this is the lowest. So from vertex 6, I am going to connect the edge into vertex 3. Okay? Now, from vertex 3 to 5, which is 35. So now, this is the minimum cost spanning tree. So remember, class, you are to select the minimum cost and you have to visit the vertex at least once. All of the vertex, okay? So it's the same it's the same. You just have to again. So another example of the minimum spanning tree. So we have this one, as you can see on the screen. So for example, okay. So I'm going to start with vertex A. So I have two different edge. I have 4. I have 8. So since 8, A going to be is the least cost, then I am going to select the edge from vertex A to vertex B. Okay, next. From excuse me, from vertex B, I have two edges. I have 11 and 8. So 8 is the minimum cost, then I am going to select the edge of 8. So vertex B going to vertex C. From vertex C, okay? From vertex C, I have to select this one, okay? Because this is the least. This is the least. So I am going to select the C to I have the 2. Okay, from vertex C. So from vertex C, okay, class. So I am going to select 4 so that I can visit the vertex F. And then from vertex F to visit the G, of course, I'm going to select this edge. And then from G, I am going to select this edge from vertex G to H, which has a weight of 1. Okay? So at least visit the vertex only once. Okay? And after that, I'm going to visit again. So from vertex C to D, okay, I have a weight of 7 here. And then from vertex D to E, I have a weight of 9. So 9 is the least cost. Okay? So objective of the minimum spanning tree. So this is iteratively construct the set of edges A in the minimum spanning tree. Initialize A to a set. So as we add edges to A, maintain a loop invariant. A is a subset of some minimum spanning tree. Maintain loop invariant and make progress by only adding safe edges. An edge is called safe for A if A is also a subset of some minimum spanning tree. So to find a safe edge, a cut, okay, is a partition of a vertices into disjoint sets S and B minus S. So edge crosses cut if one endpoint is in S and the other is in BS. So a cut respects a set of edges A if no edge in A crosses the cut. An edge is a light edge crossing a cut if weight is minimum over all edges crossing the cut. Okay, so it's just the explanation of the previous example in the previous slide, okay? So what are greedy algorithms used for? So greedy algorithms are very fast, a lot faster than the two other alternatives, which is the divide and conquer and dynamic programming. They are used because they are fast. Most of the popular algorithms using greedy have shown that greedy gives the global optimal solution every time. So now, after the minimum spanning tree, we're going to discuss the Dijkstra algorithm. Okay? So the author is Edgar Y. Dijkstra. So according to him, he have a quotation here. So computer science is no more about computers than astronomy is about telescopes. Okay? So that is Dijkstra. So born on May 11, 1930, died on August 6, 2002. So received the 1972 Alan M. Turing Award, widely considered the most prestigious award in computer science. The Schlumberger Centennial Chair of Computer Sciences at the University of Texas at Austin from 1984 until 2000. He made a strong case against use of the go-to statement in programming languages and helped lead to its deprecation. Known for his many essays on programming. So that is Dijkstra. Okay, so let's try to work this one, the single source shortest path problem. Okay, the problem of finding the shortest paths from a source vertex V to all other vertices in the graph. So we're going to use this example, this graph below. Okay, so Dijkstra's algorithm is a solution to a single source shortest path problem in a graph theory. Works on both directed and undirected graphs. However, all edges must have non-negative weights. So the approach is greedy. Okay, it uses greedy algorithm also. So input weighted graph and source vertex. So vertex is V is an element of B, such that all edge weights are non-negative. So the output lengths of shortest paths shortest paths themselves from a given source vertex B is an element of vertex to all other vertices. Okay, so this is the pseudocode of the Jitters algorithm. So distance to source vertex is 0. Okay, so for all V is an element of vertex. Okay, so do distance for the vertex. So set all other distance to infinity. Okay, so that's the meaning of this pseudocode. So S, the set of visited vertices is initially empty. Okay, next, the Q here is the Q initially contains all the vertices. Okay, while the Q is not empty, select the element of Q with the minimum distance. So that's the meaning of this pseudocode. Add U to list of visited vertices. Okay? So next, for all V is an element of neighbor. Okay, if new shortest path is found, you are to do this pseudocode. Okay? So then, set a new value of the shortest path. So if desired, add traceback code and then return distance. Okay? So that is the Jitters algorithm pseudocode. So let's have another example here for Jigstra. Okay, so we have a graph here. We have the vertices, vertex A, vertex B, vertex C, vertex D, vertex E. So as of now, we don't have any input for vertex A. That's why this one is 0. We don't have any loop. Okay, so next. Okay, now. So from A has a weight of, from vertex A going to vertex B, it has a weight of 10. Okay, that's why we have a 10 here. Next, from vertex A to vertex C, we have the edge of this one has a weight of 3. Okay, that's why we have 3 here. So that's now, since we have a weight of 10, the 10 transition to vertex B. That's why 10 is passed to this vertex. While on this vertex from vertex C, the 3 transition to vertex C. That's why we have passed the value of 3. Okay? Next. Okay, so again, we have 10 and 3 here for B and C. Next. From vertex B, we have a value of 7. Okay? Now, how from B, okay. Let's check this one first. Before, from A, okay, from A to C. From A to C, we have 3. And then from A to B, we have 10. And then if you're going to check the next graph on the next slide, how come it is now 11? It is now 7. How did it happen, class? Okay, to check the graph, from vertex A, okay, from vertex A, we have here a 3, a weight of 3. And then from vertex C, Going to vertex B, we have a weight of 4. That's why we have 7. Okay? Next. Next is what? We have the 11 on D. We have a past value of 11. How did we get the 11? From vertex A to C, we have 3. From vertex C to D, we have a weight of 8. So 3 plus 8 is 11. Okay? Next, what about 5? How did we arrive at 5? Okay? From vertex A to C, we have 3. From vertex C to E, we have 2. That's why we have 5. Okay?